All right, implementation details. This is all extremely hand-wavy, theoretical, not really relevant for the simulation work, but just some ideas and observations about if you wanted to actually build something like this that wasn't just storing a heavily discretized, digitized version of a function's values. So let's think of a function of one variable, just y equals f of x. And again, one way to think of storing a function is to just graph it. And if you have a graph of a function and it's drawn to scale and you have a really good way of measuring, if you have a particular x value, you can simply move over that much and you can measure the displacement until you find a dot, and that's the value of f of x. Now imagine, if you will, a little daemon sitting inside a cell that does this. It looks at an input value, says, okay, this is the value coming in, it measures over that far, measures up, finds where the ink is, and sets the output accordingly. All right, how would this work in C mode? And forget about the mix, because that's just an equation. But let's just talk about pure C mode. Your C input is 1. You need to do two things. You need to output the current value of the function, the current state of the function itself, and you need to input some voltage levels that turn into the new function stored in that cell. So you go into C mode, here's what this daemon does. It starts over here on the left, and it looks at the place where the ink is. It looks at the value of this waveform at x equals 0, and it sets the output voltage accordingly. At the same time, it erases this and it takes the incoming voltage and it puts a mark right there. And it moves over a little bit and it looks at the value that's here and it sets the output accordingly, and it takes the input voltage and it puts a little mark here. And so maybe the daemon has a helper. And one of these daemons is looking at the current value of this and just setting the output, turn it up, turn it down, turn it up, turn it down, up, all the way, bring it down. Right, as it investigates this over some period of time, preferably a small dt. The other daemon is looking at an incoming voltage, so it's got a multimeter and it's looking at it, and as it's reading this multimeter, it's drawing what the new value is. Oh, and the first daemon is erasing this as it reads the values. And so at the end of that time cycle, the old function has been output, and the new function has been saved. Okay, that's clearly just a working model, right? That's not how you're going to actually build this. But for me, it's been a useful model to sort of go back to and think about what's happening while a cell is operating in C mode. So, forgetting about C mode for a moment, what about D mode? How can we actually store a function of one variable and read its value out? Well, one way is to use a traveling wave. So an old guitar reverberation unit using a mechanical spring, transducer on one end, receiver on the other end. You put in a waveform and it vibrates this spring in a way based on this waveform, and it takes a certain period of time for those vibrations to get all the way down this spring. The units are typically like this big. And at the far end, so here's your spring. At the far end, you measure the voltage, the displacement of the spring, and you use that to come back in and drive a magnet, a speaker, that will vibrate the spring accordingly. Now, once you've set up a vibration pattern, you can preserve that pattern in here more or less indefinitely as long as you have power on it. So the old UNIVAC had some mercury delay line memories that went along with it, and same idea, pressure waves in this tube of liquid mercury, wave travels down here, when it gets to the end it comes back, and so you can trap a waveform. And we can use this idea to imagine how we might store a function of one variable. And in this case, C mode is very simple. If you want to do C mode, you simply break this feedback loop. You take the value that you're reading over here, and that's your output value, and you take your input value, and you use that as the sole source of stimulation for the stimuli on this spring. So C mode is actually pretty easy with this. A trickier question is D mode. So in D mode, the function is stable, so we have this feedback path. And if we want to know the function value at some point in time, we could place a sensor down here that measures the voltage corresponding to the displacement of the spring on this end. And we simply have to wait until the point of the waveform that we're interested in has traveled down to this sensor location. So let's say that this transit time is 1 second. So we're storing some waveform in here and it takes 1 second to travel from here to here. So if we want to know the function value at 0.5, we have to wait half a second, because right now this function value is in the middle of the spring. We wait half a second for that to move down here. We measure the displacement of the spring, and that's our function value. And if we want to measure the value at 0.4, we're only going to have to wait 1/10 of a second, because when 0.5's value is right here, 0.4's value is just 1/10 of a second behind. But if we want to measure the value at 0.6, which is back here, we're going to have to wait another 9/10 of a second for that to move over here. So we can measure exact readings by using a sensor at this point on the spring, but we may have to wait up to a second. Worst case, the value that we want to read is sitting right over here, and we have to wait a second for it to travel all the way down here. Now, we can get around that by adding a second sensor. And now, whatever value we want to read, we just have to wait until that value gets to one of these sensor locations. Worst case, half a second. We can add more sensors, and now, worst case, 1/4 of a second. Now, if we don't want to wait, if we want to instantaneously read a value from this stored waveform, and we have 4 sensors, we can do that right away, but there's some error in the accuracy. For example, if we want to read the value of the waveform right here, we could just say, well, let's read the value right here because that's the closest sensor. And if we're more than halfway between here and here, we could say, okay, we'll read the value at this point, and that'll be the value. And there's an error. So we're getting an error in the exposition that we're reading. We'd like to read it right here, but we have to read it at one of these sensor locations. So we have some error in delta x, but our time delay is 0. The other extreme, where we only had a single sensor, there was no error in the position we were reading because we waited until that position was exactly at the sensor, but we had a time penalty. And we can find spaces in between here. For example, if we're willing to accept a small time penalty, we can have 4 sensors in here, and we can wait for this to come all the way over to where it can be sensed, and that's a penalty of 1/4 of a second. But suppose we only want a penalty of 1/8. Well, the nearest spot to being within 1/8, okay, so if we're trying to measure a point that's exactly at one of these sensors, we can do that instantaneously. If we want to be able to measure it within 1/8, worst case is a point that's exactly in between 2 sensors. So this is 1/4, this is 1/8. And within 1/8 of a second, we're guaranteed that the point that we're interested in is going to hit a sensor if it's within here. But if the point that we want is somewhere in this half of this 1/4 region, after 1/8 of a second, the most we can do is bring it over to here, and we may have an error. And our error could be as big as 1/8. And if you do this analysis, and I'm doing it pretty quickly here and it's probably a little hard to follow, but if you think about this, the more sensors you add, you have 2 choices. One, you don't have to wait as long for the point that you're interested in this waveform to hit one of your sensors. Or you can say, I don't want to wait at all, and one of these sensors is going to be closest to the point that you're interested in, and there's going to be some error in the value that you're actually reading. Instead of reading this point, I'm going to be reading a point close to it that's accessible to one of these sensors. So we have an error in time, and we have an error in spatial location, and we can play those off each other. What we cannot do is bring them both down to 0. And the more accurately we try to measure the position, the value of the signal at some particular position, the more accurately we try to do that for a fixed number of sensors, the more of a time penalty we face. And the more quickly we try to measure the value of this waveform at some value, the more error we introduce in the actual value that we're reading. So there's something almost Heisenberg-y going on here, perhaps. And I don't know what, if anything, that leads into, but you can read about some of that in some of the publications located on the publication page. All right, let's go back to implementation. So for a one-dimensional function, f of x, we can use a traveling wave. For a two-dimensional function, we have, for example, an x and a y. And for each x, y, we need to somehow store a real number. So picture a sheet of rubber, some deformable membrane, and it has some shape like this. So it's a two-dimensional sheet of rubber. And the height of this over the plane xy represents the value of the function at some point xy. So if you want to know the function value at some point xy, go out to that position on the plane, measure how far above or below the plane this sheet of rubber is. That's the function value that's stored. Pretty easy to visualize an implementation of a particular function like this, assuming that we have some way to measure the height of this material at different points x, y, and again, a daemon inside the cell could move over and take a sounding and figure out what the function value was and set the output accordingly. To do this more practically, don't know, but it's a starting point for some sort of model for how to code a function of two variables. Now, C mode gets a new set of challenges because, again, we can't just move from one value of x to the other. We need to do some kind of raster scan because we have a two-dimensional space of x, y values that we need to cover in order to read out this function and send it through a D output, or take a D input and use it to create a new function. So picture some kind of raster scan where you start moving across very quickly in x and more slowly in y, and you just pick up the function value at each of these points, and that becomes the D output. And if you're in receiving D inputs, you do the same kind of scan and you adjust the height of this membrane at each point based on the incoming voltage level. And so you can take this function, this shape, send it out, read it back in, copy it, and so on and so forth. There's an unfortunate discretization implied here, though, in doing this raster scan, and I don't know an easy way to get around that. It may be that we can use some kind of space-filling curve to raster scan through this infinite length sweep pattern in a finite amount of time. Clearly, if we just go across and we move up by an infinitesimal amount, we're not going to cover the region in less than an infinite period of time. But maybe a space-filling curve that lets us hit every single point in some finite amount of time. Physically, though, it's really easy to make a replica of this surface, right? Just take another piece of rubber, heat it up, drop it on top so it deforms into the same shape, let it cool, take it off, you've got your new function. So I don't know if we can mimic that kind of process in some sort of automated way, and I also don't know how we would read that out. But ideally, we're not reading in and out sequentially. We're actually taking the essence of the function and just shooting that out a D output in C mode, and taking a similar essence in and using that to create a new function for the cell when the cell's in C mode. So we need to be careful to not get too caught up in the serialization that goes along with the cell matrix, and really try to think about just sort of more bulk operations. What are we trying to do take this current function, send it out, take an incoming function, plop that into the cell. All right, what about 3 dimensions? How do we code a function of 3 variables? Well, this is getting a lot harder now. So let's draw a 3 space. So here's x, here's y, here's z. And now let's think about filling this with a gas. And at each point x, y, z, suppose we can set the temperature of that gas. Not possible, but suppose we could do that so that this point has some temperature and this point has some temperature and this has some temperature. And now if you want to know the function value for some inputs x, y, z, simply go to that point in space, take a temperature reading, that's the function value, scale it, etc., all of that stuff. If we impose certain continuity conditions, this starts to be something you can almost imagine might work. Certainly we can't instantaneously change from some temperature to another temperature, so we need some kind of continuity. But you can kind of imagine if we had a way to control the temperature at all points in this space, that you might be able to do something like this. But not with any technology that I know of. A similar idea might be, instead of having a medium like a gas, to use light and something holographic to record a phase at each point x, y, z in this space, and then we could read the phase at each point, and that phase would map to the stored voltage value. And at that point, copying this function into another function is a matter of making a photograph, almost a holographic photograph, of the information stored in this 3-dimensional phase recording. If you can take that and replicate it somewhere else, you've got your C-mode operation. So those are just some ideas. 4-dimensional function of 4 inputs gets much stranger really quickly. That's another reason we've been working with 3-sided cells instead of 4. But you could start playing time as a 4th dimension and have something where you have temperature in here changing over time. And if you want to know the value at some x, y, z, t, go to that point in space, wait until that point in time, and then take your temperature reading. But that starts to get into all kinds of directions that aren't really desirable. So 3-sided cells are what we're pursuing architecturally, and there may be some possibilities for physically creating these structures. All right, that's all I have to say on sort of the background and the architecture of the Songline processor. The next set of videos is going to look at the simulation, and all the work's been done in simulation, some of it software, some with some hardware in the loop. We'll look at the software tools for that, we'll look at the hardware, we'll see some sample circuits, how to compile things. I'll talk you through the tool sets and the operations of the tools, the compiler, the configuration setup, and so on, and we'll see how we can actually explore some of these. Future videos we'll talk about possible applications, we'll talk about some of the machine learning work, and there'll be some links to publications elsewhere on the page. All right, that's all for now. Thanks.